Now let us complete our discussion of graphs with something we call as page rank. And we are familiar with this linear algebra that will make us remember matrices, which is the central concept of linear algebra. And we have also talked about adjacency matrix, adjacency list in graph. So what what we can do with this matrices are, say, we can add, multiply, we can find eigenvectors and eigenvalues. There are many more interesting things which can be performed with matrices. So what it turns out is that we have really useful meanings to these computing properties of graphs which we have learned, and some of these research in this graph theory these days is based on interesting computation with adjacency matrix, or maybe some slight variation to it. This area is known and regarded as spectral graph theory. Spectral graph theory, which is some computations applied on adjacency matrices. So one of these things naturally modeled by graph is hyperlinked test. How? World Wide Web. This is an example. Just imagine a task of writing a web search engine, which is actually the biggest problem is to how to identify not only the page which contains a particular word. Say you have a graph, a word, but you have to find the best one also. Finding a graph, a word graph in a page can be easy. But as far as this Google is concerned, it reports around 86 million result, which is far too more for us to actually check. But the ideal solution would be if this search engine which we are trying to design could actually understand the text and also find out what the page is about, that is the relevance, and whether it is useful for us or not. But understanding these languages are quite complicated, and just determining the topic of a piece of text is also very difficult. Rather than text, but finding the relevance is quite complicated. In early days, when this web came and it became somewhat popular, most search engines like Alta Vista, etc., were good, but not that wise as Google and others are, because they are only text based. They are exclusively text based only. But if you talk about Google, what is edge? What is an edge of Google? This is to look at the link structure of the web to actually find out which pages are good, relevant. And as we know that Google actually started with two students of Stanford, and after this was just a project, but competitors found it to be a serious product that can be marketed. And what Google is today. So the idea was to use links. That was the actual retrospect. So the idea behind this using link, if page A links to B, then it must have, or it must contain some endorsement from A to B. Okay, endorsement means if you are going from A to B, B should have an endorsement from A. And if you are looking at two pages, A and B, both has the same search item, as we say that we want to find out graph word. So A has more inlinks than B, then we would think that A is better than B. If A has more input links, then we can really say that A may be better than B. And this is how our draft of using links comes into picture. And once we start thinking in this realistic term, then we realize that not all links are created equal. A link which is coming to the node from the, say, New York Times is probably a stronger endorsement of a page than a link from just anybody, right? Because this does matter from which link is coming. What I mean to say is link from pages which are themselves very good, very affluent, need and should contribute more to a page which is to be considered good. So our definition has become self-referential now. So in order to know whether a page is good, we need to know whether the page linking is from good or not. And this seems quite circular, but we will see how this nicely goes into a solution. There is another way also in which links are not created equal in terms of number of outgoing links. Now we are talking about outgoing links. So we have determined that A and B are equally good pages. A has just one outgoing link to C, while B has 10,000 outgoing links, one of them to D. Then we would expect that the link from A to C confers more support because it was chosen carefully than one from B to D, which is just one among maybe a part of some directory or a phone book. So putting all this discussion at one point, we can really say that each page I has a quality score Qi, each page I has a quality score of Qi, and that these must satisfy this equation. Which equation? Qi, 1 by out degree, j is from j to I, and this is Qj. So each page, this j, confers equal fractions of its quality on all the pages it is going to be linked or it is linked to. So this is going to capture all of the things we wanted to capture earlier. So in order to make this work for the system of linear equations to have a solution, we need to assume that each page links to itself also. So we can also get this equation of linear equation in more standard matrix vector system notation like this. Let A be the adjacency matrix of the directed graph. We say that A is a adjacency matrix of directed graph, and this Aij is equal to 1 if I links to J. If I is linking to J, then this entry in this matrix will be 1, or if it is not, then we'll place a 0. And we've also seen that this will very well work if Aij is equal to 1 for all I. So how we can write is, you know why we have placed it here? Because it is Qi will be 1 by out degree from j to I, and Qj, and this is what we have written for 1, 2 until n. So this is the particular matrix divided by A. A is our adjacency matrix. So we can write this equation or system of equation like this. Q arrow will be mt transpose dot q, where this t is actually the transpose of the matrix, that is mirroring its along the main diagonal. So this standouts that Q is an eigenvector of M. Q is an eigenvector of M for the eigenvalue 1. And we can also interpret the same set of linear equation in somewhat different way. That suppose that you or any other person whom will call a random surfer starts at some node I. In each step he clips a uniformly random outgoing links from the current page. And follows that link. And he start from first point, and he continues. And because each outgoing link is taken with the probability of 1 by out degree I, he at each of the endpoint which will have with that probability after one step, each of the endpoints will have a probability after this step. So we then continue in this way, and we see that this vector transpose to the power k that is 0 0, say 1 0 0, it captures exactly the probability of being at each of the nodes after k steps. But this also present us with a flaw. What is that? Once the surfer reaches a node j with no outgoing links, except it has to have with itself, he'll never go anywhere else. So these are the only places which get stuck, and in long run, the only states that have zero probability are those with no outgoing links, right? That we wouldn't want. So let us have some good solution of this. Thinking about a random surfer to get him unstuck, we allow him to jump to a random location, that is with some probability alpha. The surfer jumps to a uniformly random new node. What do we mean by new node? Any node, whether connected by an edge or not. With what probability? 1 minus alpha. Right? The surfer follows a random outgoing link from the current page, and people typically choose this 15% or similar values. And this 1 minus alpha, which we call as a damping factor. Now let us rewrite our linear systems. This will be 1 minus alpha m plus alpha 1 by n, all ones. So this is a new transition matrix describing our modified surfer process. Now we can easily write P arrow to be B transpose P as our system of equation, or in other terms, the quality vector we want is an eigenvector of B with eigenvalue as 1. So the vector P is actually the page rank vector for the graph G, whose adjacency matrix is A. And to employ it for web search, we need to compute this page rank vector. Then sort means ascending or descending all eligible page, means all pages containing the search term by their page rank values. And the best one or the better ones will typically end up on the top. And this page rank was actually the key inside of Google when it actually started. Google has now a lot of additional ideas also with many special case treatment. That is why it is giving us the best out of billions of searches. And one can apply PageRank in other areas also. It can be used any time to link, confer some kind of status or importance. And for example, we could use it to identify some important individuals in a social network or some important servers on the computer network. So to actually compute this page rank vector, we can use this general purpose linear system solving technique like Gauss elimination method. But thanks to relatively large value of this alpha, iterative methods will converge quite fast and are probably the superior approach. So this is quite good iterative methods, at least in terms of computation speed. So we start with arbitrary vector p0, and for each iteration we compute pt1, pt plus 1 for previous pt, and as this t tends to infinity, then this pt will also converge to the eigenvector p, which we are looking for. This works for almost any matrix, because any matrix C for which the corresponding graph with edges ij, wherever Cij equal to not equal to 0 is connected. And for general matrices C, this convergence speed of this iterative method could be very slow. And PageRank specifically, iterative methods will converge fast, typically giving good approximation after 30 to 100 iterations, even for very large graphs. So this was about how we can use and how people are using this graph to solve actual real life problems. Thank you so much. Take care.